topics are maximum and minimum for graphs, and then also even-odd functions. Before we get into maximum and minimum, I'm going to talk really quickly about determining intervals of increasing, decreasing, and constant. So you actually do a lot of this in Algebra 1 just like by sight, especially when you learn about slopes, if you're talking about linear functions. So a line that's rising has positive slope, a line that's falling has negative slope. Zero slope is the constant, like the flat surface, and then an undefined slope would be like a wall, right? Okay. Now, I did make my function up of lines, so it could be a curved graph, and it could also have like increasing, decreasing, constant in a curved graph as well. When we do intervals for this, we're going to use our new interval notation. There is one big difference here. We will not have to choose between brackets and parentheses if we're determining intervals of increasing, decreasing, constant. We will use only parentheses. And I'll talk about why that is once we do a couple of the intervals. Okay, but we'll use only parentheses. And then the other thing to focus, I like how we phrased it in third hour, is we want to focus on the intervals where it's increasing, decreasing, or constant. So that would be along the horizontal axis, the x's, not how much it's increasing, decreasing, or constant. So that would be like if you were looking at the y. So you want to focus left and right, okay, when you do this. So if I were looking at this graph, I notice that on the very left side of my graph, and if it doesn't have a point right there, I assume it extends beyond the graph. And it looks like all the way from the left side of the graph, it must be decreasing. So because there was no point to say the graph starts there, my first decreasing interval begins at negative infinity. Now remember that the interval we're going to list is where the graph is decreasing, so I'm focused on the x's. What x value does it stop decreasing? -3. Okay, so I come up to that -3 value. And then remember what I said, we're going to just leave that as parentheses. So it's almost like I could draw this dotted line right there. I'm splitting my graph up vertically so I can say to the left of that is all decreasing.
Do you always leave it as parentheses, or?
In this part where we determine increasing, decreasing, or constant should always be parentheses. And I'm going to get to why that is right after we do this increasing piece. So then follow it up with an increasing section. For what interval is it increasing?
-3.
-3 to 0. Okay, -3 to 0. And the reason now why we're going to use parentheses instead of brackets is, how do you know what to include -3 in? Like if you gave it brackets on one, you couldn't give it brackets on the other. And then is it increasing or is it decreasing? How would you ever decide? At that point, x equals -3, is the graph increasing, decreasing? It's like really neither. It's sort of like turning around at that moment. That's something that you'll study in calculus. It's called a critical point. So it's a very special point, and that's why in this notation, when we're doing this task, we're going to use parentheses all the time. So we don't have to worry about which one it's grouped with. And then we would continue. There's another decreasing set from 0 to 3. And again, pay attention to when I'm labeling that decreasing interval, I'm labeling it on the x's, where it's decreasing horizontally, as opposed to its maximum to its minimum, right? That would be how much it was decreasing. I don't want to label that. And then the final section is increasing from 3 to positive infinity. Okay? You feel okay with that? The main thing would be, look over your notes one more time before you do your homework assignment and make sure you're labeling it horizontally, not vertically. That would be most people's mistake. They label the wrong section. Okay, that discussion then, increasing, decreasing, constant, leads us into the next thing we want to talk about, which is relative maxima and minima. So when it's maxima and minima, that's like the plural for maximum and minimum. And we're going to define it mathematically. Relative maxima and minima are the point or points where a function changes from increasing to decreasing. And that's kind of that point we were looking at on the previous graph as well at -3. Well, what is it doing right there? We don't really know which side to group it in with. It's not really doing either thing, it's turning around. Maxima and minima are points, so they should be labeled as such. You should always list maximum and minimums as ordered pairs, okay, just like you do for y-intercepts and x-intercepts. I'm going to go back to the previous example here in a second and refer to why we as mathematicians are going to put this adjective in front that says relative. So what do we mean when we say it's a relative max or a relative min? If I go back to my previous example, I'm going to make a point at each of the locations that I would say are maximums and minimums. So we have one here at -3, 0. We have one here at 0, 3. And then we have another here at, what, 3, -3? This is a minimum, this is a minimum, and this is a maximum. Now, each of those would really be what we would consider relative min, relative max. And what that relative really means is this point at -3, 0, it's a minimum relative to the graph around it. Okay, it's decreasing, then increasing, and it's the lowest point. It's the place where it turns around. But if we were to actually say, what's the minimum value of the graph, would this point be it? No, we would want to look at the other minimum over here. That's the actual minimum. To talk about the real minimum or the absolute minimum, we use the phrase global. So it's not just relative to the graph around it. A global minimum is for the whole function. And the same would be true of this maximum. It would only be a relative max, because what's the actual max of this graph? Positive infinity. There is no maximum, really. It just continues to go on forever. So that's what that phrase means right in front. And that's something, again, a discussion you have more often in calculus, the difference between relative and global. Now, how we find max and min, certainly if you have a picture of a graph, you can look at the picture and you can identify the location of the max or min. If you have just a function, you could use your graphing calculator. So that's what we're going to practice. In calculus, you'll also get more into like the mathematics of finding those max and mins. Those critical points are going to be how you find that. And so we don't really have the capability, like for any polynomial, to algebraically find the max and mins right now. We would need a graph and be able to either pinpoint it on the grid or use a calculator. We could find max and min, however, for quadratic, because we know how to find vertex, and that's always the max and min of a quadratic. So we do have that capability algebraically there. These are a list of, or the series of instructions I would tell people if they're finding max and min on a graph, and I mean on your graphing calculator. I'm going to teach the graphing calculator as if everybody in here is using a Texas Instruments calculator. So if you're not using Texas Instruments, you'll have to, kind of use Google or step it into me before after school if you're not able to find those specific buttons on your calculator. But we'll definitely make it work. Okay, I'm going to put up an example function, and I'm going to get my calculator. If you need those words behind my calculator, they're just min and max. Now, if you're using one of my calculators that I loaned out, there might be something on the screen. You can usually just type clear to get out of it. And that may mean when we get to graphing that your zoom is different, because we're going to mess around with our zooms as well. Okay, anytime you want to do graphing on the TI, you're basically using the 5 buttons right underneath the screen. Those 5 buttons are for graphing. Okay. The most important button to get started is the y equals button on the left. So go ahead and type y equals. If there's anything in the y equals menu, go ahead and type clear. Even if it's the same example, it will give you practice for typing in. And note that everybody's calculator at this point should say y equals in that menu. If yours says like r equals or anything different, let me know. I need to change the mode. If it doesn't say y equals, we're in the wrong mode, and that would probably be my calculator. Okay, now you've got to input the function. Remember that TIs are really picky about negatives and subtraction signs. So the negative is down by the decimal. Oh yeah, listen to what I'm saying right now. The negative is the one by the decimal, and the subtraction is the one over on the right column with the other operations. So to start this off, we have to choose negative, not minus. Okay, so make sure you choose the one by the decimal. And then to get the x, I know that you have the alpha key, but actually right next to the alpha key, most of your alpha keys are green. You see the button that says x comma t comma theta comma n? That's the variable button for the function, or for the graphing function. So anytime you want a variable in there, just hit x comma t comma theta comma n, and up pops your x. If I change my mode, that's when I might get theta or t or n. Okay, so you should always get x in function mode. And then type the rest of it. I'm going to square it using the square button. Plus 13. To get my x, just type x comma t comma theta comma n. And then this time minus 2, I got to use the subtraction, not the negative. So the one on the right column, and then 2. Even take a minute to look at the negative and the subtraction on this slide. Do you see how one is smaller than the other? If you ever hit enter in graphing or in regular mode and the calculator says something about syntax, if you select number 2, it will say go to. It'll go and blink right on the thing that's wrong, and it'll probably most likely be blinking on like a negative or a minus sign, so it means change it. You can just override it. Leah, did that help you?
Yeah.
Okay, so now just hit graph. Well, I'm going to do and change mine real quick. Most of yours probably looks like this. Okay, it looks like a line, and I know that that graph is not supposed to be a line, correct? For most of us. Okay, so we know that that's quadratic. We know that it should be a parabola because it's negative. The parabola should be opening down. And I can kind of tell I'm probably not seeing my whole picture. So I want to change my zoom. This would be good for you to just kind of play around with on your own, like messing around with Zoom and seeing what kinds of things you can do. In Zoom, you have a couple of options. On this one, I want to zoom out, so I'm going to choose Zoom 3. And then you look at it and you're like, it didn't zoom out. Notice at the origin, there's like a little blinking dot. And it's saying like, where do you want the new center of your graph to be? I'll zoom out from there. So if you want to move your cursor and have it uncentered from the origin, you could do that. I'm fine with mine being at 0, 0, so I'm just going to hit enter. And now it's going to actually zoom out for me, and I get the parabola. Okay. At this point, I can go back over here to the steps I want to take. Now I want to calculate the maximum value of that quadratic, so I'm going to do second trace. Out of batteries? Hit second trace. And then choose whatever it is you're trying to find. Here we want a max, so second trace, and then I'm going to hit 4. And now it's going to ask me, if you notice in the bottom left corner of the screen, it's asking me a series of questions. was the left bound of your maximum, was right bound of your maximum. So now you have this blinking cursor that looks, I always think it looks like a spider, even though it only has 4 legs. Move that closer to your maximum, but stay on the left side of the maximum. So if I'm not sure if I'm on the left side, move your cursor so that you're on the left side of the maximum.
How do we move the cursor?
Left and right arrows. You didn't put your square.
Oh, I moved it.
So the second you leave, we'll let you insert.
I think, but like, you have to make sure it's on the left side.
Okay, I'm on the left side of my maximum, so I'm going to hit enter.
Should we go like all the way down? Yeah.
You want to get closer to the max. So like here's your maximum point. The calculator is going to ask you for a left bound and a right bound. You're going to say this point's on the left side of the maximum. This point's on the right side of the maximum. And the calculator is only going to search for your maximum right there. So you're just helping him out. Her out. Wherever the maximum is. Okay. So now it asks me what's the right bound. I've got to go to the right. And I'll hit it as many times until I'm like pretty sure I'm on the right side of my maximum, and then hit enter. And it even puts like these little arrows on the graph saying like, this is, you want me to guess in between these 2 arrows? And you're like, yes, please guess. I want to know the maximum. So hit enter one more time. And I get like 6.499999. I could say 6.5, right? So my max is at 6.5, 40.25. So a lot of times it will do that, like it'll get close, but it will kind of leave that trail of 9s or 0s. And so you can round it at that point, definitely. Does anybody have any questions about that process? If that's a polynomial and there's other relative mins and maxes, then you just repeat for the new one. You have to do like left and right around each one, not around the whole graph. Okay, so you have to like attack each min and max separately. Okay. Now, before we leave our calculator for good, I'm just going to make a note on the next slide that you can also use this to find zeros. So some of you might have noticed when we did second calc or second trace, the calc menu, there's a lot of other options on there. Function values, zeros, mins, maxes. So you can do more than just min and max there. This is the same set of directions. The only thing that has changed is you should choose 0 instead. And remember, we talked about zeros on Thursday. Finding zeros would be like finding x-intercepts. So if I bring my calculator back up, if it was a question where I was allowed to use a calculator and I was asked to find the zeros of this function, instead of having to factor or quadratic formula, I could then choose to do second trace, get the calc menu. This time I want to find an x-intercept or a 0, so I hit 2. And it's asking me the same 2 questions. Left bound, right bound is going to do. This time, like if I want to find this 0 right here, then I have to get to the left side of that 0. So my cursor is back where I left it for my maximum. I got to backtrack. So 0, negative 2 is on the left side. I'm going to go ahead and hit enter. My right bound, I'm going to move it so I'm like 0.85. I'm past that. Hit enter. Guess it. Yes, I want you to guess it. And it looks like I have a 0. It says 0.11 or 0.1557. So I'd say like 0.16. I'd round to the hundredths at least. If I want to do the other 0, then I got to go around the maximum and down by that 0. So a good little activity just for you to kind of see what your calculator can do. And it'll be a good way for you to kind of like check your answers or see things about graphs that you want to know. Does anybody have any questions about that calculator work? Okay, also I should post a video about the about our notes today, so you could go to the video and you could watch one more time if you kind of forgot how it worked. Okay, that's it for calculator stuff today. So you can set your calculator to the side. We're going to move on and talk about even and odd functions. Remember that on that pink sheet that I gave you last Friday, it was the last column says even, odd, or neither. After today, you could take another look at that and see if you could fill in that column. Remember also I noted like the greatest integer function, the last function on that library function. We will do that tomorrow as a class. So if you want to hold off on the greatest integer function, you can just fill that in when we do it tomorrow. Okay, but the other functions you should know from your previous math class. They're on the summer packet. And you can also find them in the back of your textbook. So there's some information there.
It'll also be right next to the like examples for our homework class Friday.
Oh, it was? Okay, good. Okay, so the question of even, odd, or neither has to do with symmetry. If it's an even function, it's symmetric with respect to the y-axis. So it's got vertical symmetry, but even more specific, it has to be vertical at the y-axis. So if this parabola was like shifted right 5 units, it would not be an even function. Okay, so an even function has to be symmetric to the y-axis. I'm going to, on that quadratic function, I'm going to take a few points. I'm going to ask you to look for a pattern in the x's and y's of points that are on the symmetric pieces. So I'm going to say this point right here looks like it's at 1.5, negative 3. And then on the other side, there's a negative 1.5, negative 3. This point right here looks like it's at 1 positive 1. 1, 1. And this point right here looks like it's at negative 1, 1. Okay, so when you look at those two pairs of points, what are you noticing with x and y?
It's just negative.
What's just negative?
It's like opposite. Like the x is negative, or positive.
The x is opposite, the y is the same. Okay, so that's really important. In an even function, it would be true that the 2 points that are like symmetric to each other, the x's change signs, but the y's stay the same. So here's going to be your algebraic test for even functions. Does f of negative x still equal f of x? Remember, f of x is a fancy way to write y. Okay. So does f of negative x still equal the same y? And I'll show you on the next slide, we'll do an actual example with an actual function. What does that actually mean to do that check? Okay, but that's what you're looking for. The next type of function is that odd function. And odd functions are symmetric about the origin. So in geometry, you might have called that type of symmetry like a rotational symmetry. If I look at that blue graph that is odd, I can't reflect it over the y-axis, I can't reflect it over the x-axis and make it map onto itself. But you could imagine, like, if I were able to take that blue graph and just rotate it at 180 degrees, it would then be itself. So that's what it means to be symmetric to the origin. I'm going to do the same thing and pick out a pair of points. This one looks like it's at 0.9 and negative 2.1. And then this one looks like it's at negative 0.9 and positive 2.1. And that's hard for you to see. But what are you noticing about x and y now?
The x is same, and then this is 1.
Angela says, so quietly, the X and Y are opposites. So now they're both opposites of each other, okay? Which is going to change our algebraic test. Now we want to know if we put in the opposite of X, so f of negative X, is that the opposite of Y? Negative f of X. On your homework, I want you to do the algebraic tests. You can use your calculator by graphing the function to confirm if your test really told you correctly, if it is symmetric to the y or it is symmetric to the origin. But I want you to do this algebraic step. I'm going to show you how to do that here on the next slide. So here's our function. F of x is equal to 2x cubed plus 3x. Okay, so now we know what y is normally. Y is 2x cubed plus 3x. We're going to do our first check. I'm going to check for an even function. And my check for even is, if I do the opposite of x, will I get the same y? So that it's symmetric to the y-axis. So does f of negative x still equal f of x? Which means I am going to go to this function and I'm going to do f of negative x. I sub negative x in everywhere I see x in the function. Just like if it was f of 2, I would just put 2 in everywhere. So 2 times negative x cubed plus 3 times negative x. Now, if you don't simplify, just looking at it right now, it definitely does not look the same as the original function, right? Because instead of x's, it has negative x's. But it's your job to simplify those negative x raised to exponents. So you're basically just going off of patterns of positives and negatives. If a negative number is raised to an even exponent, what kind of number do you get? A positive. If a negative number is raised to an odd exponent, what kind of number do you get? Negative. So you're going to just use that to help you determine what these terms are going to simplify to be. Negative x cubed is going to be negative. Times the positive 2 is going to turn it into a negative. So this first term is really negative 2x cubed. And then plus 3 times negative x is negative 3x. So now when I look at this f of negative x that's been simplified, is that exactly the same as f of x? No. Okay. So f of negative x does not equal f of x. It's not even. If it were even, I could stop. Since it's not even, I continue my check. Now I'm going to check if f of negative x, which I already know, is the same as negative f of x. So I really only have to do one more thing, right? I have to figure out what negative f of x is. What does it mean when you put a negative in front of the function notation? What am I making negative? The y, the whole thing. So when I want to make this whole function negative, because this is the y value, I'm going to have to put a negative and then a group of parentheses. Follow it up with the function. So I'm making all of f of x negative. To do all of something, use a group of parentheses.
And then we distribute the negative.
And then we distribute the negative. So then you get negative 2x cubed minus 3x And that's the same thing, I have it covered up right here, but those two things are the same, f of negative x and f of x. So I'm focused on f of negative x and negative f of x. They both simplify to be negative 2x cubed minus 3x. So no matter what x I put in, I'm going to get out that same thing, that negative f of x. So f of negative x is equal to negative f of x, which means it is odd. Now, if that didn't work out, if they weren't the same things, what would you then decide? It's neither. If it did work out on the very first one for even, then you would stop. You wouldn't have to check odd as well. We okay with that? Okay. So those will also be on your homework. And like I said, if after this you wanted to type this function into your graphing calculator, you could do that. I'm actually going to do that real quick. What is that? 2x cubed? 2x cubed. Oh, I gotta do that thing. Oh man. It's not too bad at this part. 2x cubed. Math print is not my specialty. And the smartboard as well. Can do it plus 3x. Okay, and then I'm going to zoom 6. Remember, zoom 6 is standard, so it'll always go back to negative 10 to 10 on both axes. Does that look odd? Yeah, it looks like it would have rotational symmetry, so that corresponds with what we said algebraically. Your homework assignment's on your gold sheet. Okay, just as a reminder about homework, bolded and underlined is required, so I am expecting you to do those when I come around. Those should be completed. The other ones are still recommended, so especially if you're feeling uneasy about a particular section, you should do all those problems so you can ask more questions. For your problem set, which you're going to get your first problem set tomorrow, I can choose any problem from the assignment. It doesn't have to be a required problem. Okay, so it is in your best interest to do the whole assignment. And that's on your gold sheet, so you don't have to write it down. You should just look at today. Today also says reflection questions. That has to do with your quiz, but in interest of time, we're going to save that for tomorrow. So you'll get that tomorrow. If you want to cross reflections off of today, you can do that. And then if you could try to come with your pink sheet filled out tomorrow, that would also be great. So